Okay, so I should thank Kirill for asking me to talk, although I have slight misgivings. Not as many as Dave has about this material, but thankfully he's not here yet. So, okay, so I want to talk about ambitwists and strings in 4 dimensions. And for me, this is a story that goes back to my thesis. And in fact, of course, it goes back sort of quite a long time before my thesis. So the ambitwister story in 4 dimensions was initiated by Witten and by Eisenberg, Yasker and Green in '78. And the basic idea was to extend the Penrose and Ward nonlinear constructions for self-dual Yang-Mills and gravity. And of course, those were beautiful constructions. They encode the general geometric information of a solution to self-dual Yang-Mills or gravitational equations just into pure deformed complex structure of a complex manifold, to some region in CP3. So it gave a beautiful paradigm for how twistor theory was going to interact with physics, and but of course the self-duality restriction meant that it couldn't really, it wasn't going far enough. It was only dealing with circular polarization. And so in '78, in '78, the ambitwistors were introduced. They're essentially a cotangent bundle of twistor space, but they're also complex null geodesics. And by complex null geodesics, I mean it's quite radically complexified in the sense that you're looking at null geodesics that are going off not just in the sort of TZ, t equals z direction, but also in the x plus iy direction. So you're really allowing things to shoot off right into the complex. And you maybe start thinking about having a real spacetime that you analytically continue, and you think about all of these complex null geodesics all at once. So so '78 was Yang-Mills. Gravity took quite a lot longer. So Claude Lebrun set up the sort of general framework. So the story here has 2 steps. In the original nonlinear gravitable construction, the existence of the twistor construction gives you the self-duality equations, whereas here the Yang-Mills correspondence and the Einstein correspondence work without any field equations being satisfied, and you have to characterize those ambitwistor spaces or bundles of ambitwistor space that satisfy the field equations. And so this was something I worked on in my thesis, and Claude Lebrun sort of finished the story in '91. And I'll tell you a bit about what that story actually is in detail later. But suffice to say at this point that it was sufficient of a mess that, it wasn't a mess, it was a clean statement. I make those clean statements, but it's difficult, especially difficult to use, that people essentially drop these constructions. And in fact, as far as I know, there isn't really a non-trivial example of these constructions in existence. I mean, I think Stefan is just now probably putting together the first non-trivial curved example of a deformed ambitwistor space. I'll talk about that classical story in some detail, because I'm meant to be sort of talking to geometers as well today. But then what I think brings that whole framework to life is the more recent work on ambitwistor strings, which really started life as twistor strings. So this is of course with Witten, Berkowitz, and so on, started in 2003 and 4, and so there are these beautiful formulae for scattering amplitudes, and these somehow telling you that there's something very beautiful is going on in relationship between ambitwistors and gravity, which couldn't really be guessed from these earlier results. And
when you say non-trivial examples, I mean, if you take a simple non-self-dual plane wave and you solve from null geodesics, why isn't that an example?
Well, okay, but you've got to sort of go through the whole thing of reconstructing the quadrics. And there are lots of trivial examples which are cotangent bundles of twistor spaces where there are lots of beautiful examples. But so you want something that's not self-dual. And I mean, you're right. I mean, it would be very easy to do for the plane wave. But it's already quite subtle for the, I mean, I'm not going to talk about it, but it's already quite subtle for the Sporchart solution, where you've got some elliptic vibration and it's given the ambitwistor space is given by, well, sorry, I mean, it gets complicated, but yeah, but something like this Fortschritt you'd expect to have been sorted out years ago. Okay, so the well, the twistor string was called a twistor string. It wasn't really ambi-twistors, but then these the story evolved. Twistor string got extended to supergravity, but firstly as a formula, and then as a string theory by David, and but then Casazo, Songhoon, Ellis Yuan extended these things to all dimensions for gravity, Yang-Mills, and plenty of other theories. And David and I were able to see that these came out of string theories in ambi-twistor space. And this was quite nice. It actually placed the original twistor string in that context. So in this sort of multi-dimensional context now, because the basic Lebrun correspondence worked in all dimensions, but the characterizations of the field equations were adapted to 4. So it allows you to go back to 4 dimensions and say, well, was the twistor string the only way of doing things? And sort of one of the targets of today's talk is to say, well, no, it wasn't. There was actually an ambidextrous way of setting up an ambi-twistor string theory in 4 dimensions. And so this is something that was done with Yvonne and Arthur. But, yeah. So just for those who haven't seen it before, I mean, the motto here is that these things are, although they're string theories, they're holomorphic string theories. A standard string theory is a sort of minimal surface. It's not necessarily holomorphic. So they're what you call chiral string theories. But they have none of the richness of string theory. So none of the beautiful things that Chris was telling us about this morning. No T-duality, alpha prime is 0. So for some people that'll be a good thing, and for other people that's a bit sad. Okay, anyway, so just to set the frame a little bit, we're talking about null geodesics in the real context. I'll just give a Lagrangian formulation to start off with. In the real context, you think about you often think about a first order action or a phase space action, where you start off with a cotangent bundle of space-time, you have a curve in that cotangent bundle, and you can write down an action that looks like this. And here E is an ion bind, P is the momentum, and this is a multiplier that tells you that P squared vanishes, so you've got a null cotangent vector along the geodesic, but it also plays a role of a gauge field, which gauge transformations shoot X up and down the string. Up and down the null geodesic. So this is a Lagrangian way of talking about the Hamiltonian reduction of the cotangent bundle of M to give you the space of real null geodesics. Something quite nice happens when you complexify this. So if you complexify, then of course your null geodesic is going to become a one-dimensional complex manifold, and you have a bit of choice as to how you're going to think about it. So we're going to make complexify a real manifold and its metric to become a complex manifold, a holomorphic metric on the neighbourhood of the real slice. And then we're going to think about a map from the Riemann surface into the space-time, and it's momentum P. And we can write down the same thing. Now, I guess if you really wanted a complex null geodesic, you'd have had d by d holomorphic parameter here. But for the ambi-twistor string later, we'll actually have a d bar on this Riemann surface. And so what this is actually going to give us is a, well, we're going to have a similar story to what we had in the real case. This E here is going to play the role of Lagrange multiplier enforcing P squared equals 0. But it will also be a gauge field whose gauge transformations send you up and down the null geodesic in the complex. And so if you quotient out by the gauge, you set P squared equal to 0, and you're actually sitting on the space, on the ambi-twistor space. But this will now actually give us a holomorphic map from the Riemann surface into ambi-twistor space. So you get something for free here. You're getting a whole holomorphic curve in ambi-twistor space. Okay, so this is a precursor. This is a classical story, and it's a precursor to the string theory that will come later. But I want to just talk about the classical geometry of ambi-twistor space. So, as I said, as I said, ambitwistor space then is the cotangent bundle divided by the null geodesic spray p dot nabla. So this is a statement you can make in curved space-time, and the p squared is of course the Hamiltonian for the null geodesic spray, and as a consequence, the symplectic form dp wedge dx descends to ambitwistor space, and a feature of the null case is that we also have that the symplectic potential descends. So the contraction of theta with d naught would not vanish if p squared is not 0. So we actually have these two structures, the symplectic potential theta and the symplectic form. Now, ambitwistors were meant to provide a non-self-dual generalization of the Penrose nonlinear graviton construction that is encoding the geometry of spacetime into the deformed complex structure of now ambitwistor space. As defined here, well, in order to sort of run the Lebrun machinery, we tend to quotient by the scaling. So this A was a space of complex geodesics with the scale of the associated momentum vector, but we can projectileize out by that scaling. And if we do that, then we can't really talk about the symplectic structure because this is not orthogonal to the Euler vector field along P, but we can still talk about theta, and we can also encode the non-degeneracy of the symplectic form by saying that theta is a holomorphic contact structure. And this introduces a line bundle as well, so it's a line bundle valued form, really things with scaling weight 1 in P. And the Lebrun's theorem was to say that it's the complex structure on this manifold PA that actually can be used, that does determine n. It contains the entire information you need to have to reconstruct the metric. Well, when I say the metric, just a conformal class in this format. And the correspondence is stable under arbitrary deformations of the complex structure. But in fact, if you do a completely arbitrary deformation of the complex structure, what happens is that you get, when you reconstruct the space-time, sorry, so I should say a little bit about how that works. So, what is it? Is that an automatic thing that happens when I lift the board?
Yeah. Yes.
Oh, okay. That's very clever. Okay, so we have space-time here. We have a point x, we have a light cone, and the light cone in space-time corresponds in the ambitwistor space to a just a subset, which is in the projective ambitwistor space. This is really a quadratic, so we think of it as so if we're in d dimensions. Here, this is a d minus 2-dimensional quadratic, and this is a compact complex manifold. And so what Lebrun does is he shows that these quadrics come in a d-dimensional family in general, except when d equals 3, when you get an extra parameter that you weren't expecting. That modular space is the original space-time, and you reconstruct the metric just by intersection of these. So this is, for 4 dimensions, this is a 5-dimensional space. So this is M4, that's 5-dimensional. These two quadrics in 4 dimensions, with intersecting the point corresponds to the existence of a light ray between those 2 points. So you reconstruct the formal structure, but what happens is that if you don't preserve the symplectic potential, you find you have null geodesics for a torsion connection. So if I pull this down, will the amazing. Okay, so if you're just interested in conformal structures without torsion, then you have to preserve this symplectic potential. so the upshot of this is, in fact, the complex structure of ambitwistor space is actually, in the case that we're interested in, determined by this one form, theta, because it's a contact form. Theta wedge d theta to the top power is a non-degenerate holomorphic volume form, and therefore annihilates all of the anti-holomorphic vector fields that make up the almost complex structure. And so you can think about parametrization. You can parameterize the variations of the complex structure just by variations of this theta, if you want them to preserve the existence of a contact form. And actually, for some reason, the time is advancing. I was going to run through the Penrose transform here to show how it works, but maybe I shouldn't. Sorry. The time's advancing. So such a thing. I mean, what's slightly surprising here is that this theta is p dot dx. You can't see the metric sitting in there. I mean, that's a downstairs index. That's an upstairs index before you start. But the variation of theta does indeed contain information of the metric, and you can run through the process here, say for a plane wave, ECI k dot x, and you discover that delta theta varies by this quantity here, going through the Penrose transform. And what was important for the CHY formally and the ambitwistor string story was that this Penrose transform actually built in the scattering equations, which play a big role in the. So this is, in some sense, where you see the entry of the scattering equation. So something very non-trivial is happening there by taking this transform from space-time to ambitwistor space. Okay, but that all comes later. That's all for the amplitude formula. That was a conformally invariant framework, and it turns out for the string theory, you want to actually consider null geodesics with spin. And there is a standard model for that, whereby you throw in a fermionic vector along the world line, a spin vector, and you see in geometrical quantization, when you quantize that, you impose a constraint that p dot psi equals 0, and that will become the Dirac operator. So this is one way of introducing spins in the spirit of the RNS, and you can write down the super ambitwistor space, and based on this, so this is a construction you can do in all dimensions, and it gives you a manifold with 2D minus 2 odd variables, and a symplectic potential with some odd parts to it. And you can also follow through the Penrose transform and understand how the super-Lagrange correspondence works in this case. And this actually gives you everything that you need for an S gravity for a B field, as well as for a metric and a dilaton and so on. So in fact, for the 10-dimensional ambitwistor string, this is the ambitwistor space that we're most interested in. It's the one with these extra fermionic variables. Okay. Anyway, there are lots of other models, though, about ambitwistor spaces. You can use a Green-Schwarz type model to make it supersymmetric, or you can use pure spinners and so on and so on. There's lots of ways of coordinatizing null geodesics in various dimensions. You can adapt to the geometry of null infinity. But what I want to talk about today is how you can think about this in 4 dimensions by solving the constraint p squared equals 0 and reducing classically, and then quantizing. So that so if you sort of try and quantize, what one of these, this sort of string here, then you've got to worry about this constraint p squared equals 0, and you've got to do some BRST stuff on the gauge fields and all that sort of thing. You can avoid all that if you can solve the constraints. And there's a standard way to do that in 4 dimensions using twistors. So the okay, so I assume everyone here is familiar with spinners, two-component spinners. Everyone's happy. Okay, so so the first thing to do then is to solve the constraint p squared equals 0 with two-component spinners. You write p equals lambda lambda tilde, and of course lambda and lambda tilde are now freely prescribable. You do have a phase redundancy between them, and that will play a role later. And we want to sort of quotients by x goes to x plus lambda lambda tilde. So we want to do that quotient. And so you can do that by adding a pair of spinners, mu and mu tilde, by these relations here. And it's easy to see that that's invariant under this translation up and down the non-geodesic. You actually can see here, I mean, in 4 dimensions though, this x, a, alpha dot is 4 components, and so the and the mu's are 4 components. So in some sense we've got a redundant variable in here. So one way to so what that means is that these coordinates lambda tilde, mu tilde should satisfy a constraint. So we organise them as a twister, lambda mu as z, and mu tilde lambda tilde, w as a dual twister. And so this is dual by the relation that z dot w should be equal to this quantity here. And this redundancy that we've built into this definition of mu and mu tilde here is encoded in the fact that z dot w equals 0. We would furthermore have so if you substitute these two relations into here, then that will automatically be satisfied. If this relationship is satisfied, you can solve for x. So that's the point there. So one of the key, you still have some redundancy also in the overall phase of lambda and lambda tilde, and that will factor through into an overall phase for z and the inverse phase, w. So this gives you a description in 4 dimensions then of ambitwistor space of complex RD digits as t cross t star, subject to z dot w equals 0, and then quotiented by this phase, z dot d by dz minus w dot d by dw. So that's and so this here is just an algebraic relation you can prove immediately. It's either it's a sum statement. Okay. I've been worried about time earlier. I think I shouldn't have decided to finish early, but I realised I was worried. Okay, so how do you understand field equations? Well, in 4 dimensions, then we've got this picture whereby the ambitwistor space is a. So one way that you would say it is that we have this PT star, and you think of ambitwistor space as being some big quadric z dot w equals 0 inside PT cross PT star. And one of the ways that you exploit that to understand the field equations is that you can start talking about whether objects on ambitwistor space extend into twistor space, the product of twistor space and its dual. And there's a rather elaborate mathematical machinery whereby you set up things as complex analysts or algebraic geometers know as formal neighbourhoods. And this is actually, in some sense, morally quite a straightforward idea. You're talking about trying to extend structures of ambitwistor space into the product of, sorry, there's meant to be a star on there, and I somehow managed to miss that out in both cases. Twistor space across its dual, but you only do it to a finite order, so you go up to order k plus 1. And so what, so Iceberg, Yaskin and Green, first of all they managed to show that any old Yang-Mills field would give rise to a holomorphic vector bundle on ambitwistor space. And in fact, there's any holomorphic vector bundle ambitwistor space determines an off-shell Yang-Mills field. So it's a two-way correspondence. And so then the question arises as to how do you express the field equations? And somewhat surprisingly, you discover that the field equations are best expressed as the condition that this holomorphic vector bundle E over ambiguous Twistor space should extend to, that K should be 3 now, I'll tell you how I slide and do, to the third formal neighbourhood. So, I mean, roughly speaking, what happens is, if you think about it in terms of linear theory, you might have some, instead of having a holomorphic vector bundle, you might have a line bundle defined by a cohomology class. You ask the question, have a cohomology class ambiguous Twistor space that corresponds to a Maxwell field that doesn't satisfy any equations. And then if you want it to extend to PT cross PT star, the cohomology, you might have an H1 of ambiguous Twistor space and with values in the line bundle O. And if it actually extended to the Cartesian product, so if you had an H1 on PT cross PT star, you have a Kunith formula that tells you that that's equal to H1 of PT times H0 of PT star times the other plus the other way around. But then once you actually PT tensor H1 PT star, and so this is just a simple Kunith formula, and so it's, the H0 of PT is just a constant. So what it's telling you is that the a line bundle or cohomology class on the product is necessarily just comes from a cohomology class on Twistor space or dual Twistor space, and hence is necessarily the sum of a self-dual and an anti-self-dual field, and hence satisfies the Maxwell equations in that case. And so then you can ask the question as to, well, what order does that kick in? If you start extending this order by order, when does this actually happen? And it happens to happen at third order. So that was the original sort of Eisenberg, Yatkin, and Green argument. This has an extension to gravity, so this is one of the things I worked on in my thesis. And so you can so Rob Basson and I did a linearized and second order analysis, and we discovered that the conformal gravity equations are satisfied if and only if you can extend the underlying manifold to fifth order. And then Einstein came about, if the curvature was general, if you could extend to sixth order. So that was, it's a slightly odd result, but anyway, that was the definitive way to express the field equations as of the 80s or early 90s. But
so if you can extend to seventh order, is it always either self-dual or anti-self-dual?
Well, actually, I was just realising that was it was already pretty hard getting the 5 to 6 obstruction, and the 6 to 7. I was just realising as I was sort of writing this that we were not courageous enough to push it that far. I mean, he was already stretching the limits of calculation to get to this one.
Am I right? I can't quite remember. In Yang-Mills' case, if it goes to fourth order, then it's either self-dual or anti-self-dual, and it goes all the way.
Well, what you get is so fourth order, you get F plus with F minus commutes as a so that's the self-dual part of the curvature and the anti-self-dual part of the curvature. So that's that's quite a strong condition. You really don't want to require that. So fourth order is already sort of not good for Yang-Mills. But it may be that Einstein is just nice enough that it goes to 7. Because this, so if I say the rest, then we'll see that there is a mismatch. So so you can actually supersymmetrize Twistor space just by adding on n fermionic coordinates. So this is a standard thing to do. And and there's a correspondence between these formal neighborhoods. So the point is that, so if you've got Z I is equal to sort of your lambda mu and then chi, and similarly for W, mu tilde, lambda tilde, chi tilde, then what happens is that you have the supersymmetric Z dot W is, maybe I should try and do a calligraphic Z dot W. So the supersymmetric Z dot W is equal to the non-supersymmetric Z dot W plus chi dot chi tilde, where the chi and the chi tilde are fermionic, and this term here satisfies the property that chi dot chi tilde raised to the n plus 1th power equals 0. So if you say that the calligraphic Z dot W equals 0, so if you're on the supersymmetric ambitwistor space, then that turns out to be the same thing as saying that you're on the k formal neighborhood. So that's this statement here with the typo. The PA sub k, k formal neighborhood corresponds to k, n equals k supersymmetries. And so Witten at the same time as Eisenberg and Gattingen and Green came up with a similar result, but in terms of the supersymmetric Yang-Mills series, it's calligraphic n equals 3. And so that's actually, maybe following, is probably where your question was leading, this story is actually unfinished for gravity because, first of all, this is a statement about the fact that for n equals 3 Yang-Mills, the constraint equations for the supersymmetry imply the field equations, and I don't know whether that story is completely tight for gravity. And are you getting the field equations for gravity at n equals 6 or n equals 7? And I think it's, I just don't know, maybe there's some supergravity expert here who knows the answer to that. But, so I think there's maybe just a little bit of a loose end as to how these supersymmetric formulations work for gravity. Okay, so without giving any formally, I can just say that you can use these constructions to write down twistor actions for, ambitwistor actions for Yang-Mills theory on ambitwistor space. So you can either do it for the formal neighborhood case or for the supersymmetric case. And the way in which you do it is to somehow say that, you see, for the supersymmetric case, it's anitas, because you are just saying that the curvature should vanish, and that's what the field equations for the 0-2 part of the d bar equation should vanish, and that's what the holomorphic Chern-Simons theory field equations are. And there's a subtlety there, of course, that holomorphic Chern-Simons you'd have thought only works in 3 dimensions, but what happens here is that you have to restrict to a real slice of those nullity digits that intersect a real slice. And if you do that, then you find there's only 3 remaining anti-holomorphic directions. Okay, so you can set up an ambitwistor action, this should be ambitwistor action on ambitwistor space, for n equals 3 Yang-Mills, but as far as I know, there hasn't been a single non-trivial calculation with that. Is that true? Unless you've done better than me. Okay. So anyway, so ambitwistors are sort of tough to actually apply to real-life problems, at least in this classical geometric framework. Okay, so so if we go back to the idea that I was talking about at the beginning, that you could think about a string theory in ambitwistor space of just holomorphic strings, and that might give you some interesting insights, then what that string action was based on was the contact structure. You basically sort of put d bar instead of d inside the contact structure, and that is the action for the ambitwistor string. And you have to make sure that W and Z, I haven't really specified things very completely, you have to maybe I'll just write stuff at the top of the board here and So I guess in the standard ambitwisted string, we have p dot p bar x. X is a scalar, but you have to say that p is a one form on the Riemann surface. So we've got to have, if we've got z dot p bar w, if that's going to be an action, we can iterate by parts just to get left with one z and w. We can have z and w in line bundles L and L tilde, L tilde over sigma, such that L tensor L tilde is a one form. So that's part and parcel of setting up an ambitwisted string, specifying line bundles for W and Z. I've thrown in an extra term here, A times Z dot W, because you want to have A being a Lagrange multiplier to set that Z dot W equals 0. And the gauge associated to that Lagrange multiplier will also shift the phase of Z up and the gauge and the phase of W down. So we'll end up with ambitwisted space properly after you've done the quotient. Now, with n equals 4 supersymmetry, this is actually essentially identical to the Berkowitz-Witten twistor strings. You can integrate by parts there. Here it does have w dot d bar z, but that's sort of z dot w is 0 anyway. So it's essentially equivalent to the Berkowitz-Witten twistor string. Except for the Berkowitz-Witten twistor string, what you're doing is you're always making this one negative and this one positive as a line bundle on the Riemann sphere at least, so that the W is always 0. So with that, you get W equals 0, and it's really a twistor string in terms of the actual solutions you get. And as we know, we can get beautiful formulae for Yang-Mills amplitudes, or in the case of gravity, David's model, gravity as well, or conformal gravity if you're enthusiastic about conformal gravity. But if you want to think about this ambidextrously, you sort of ask the question as to what happens if Z and W are both spinors on the world sheet. They both have weight -1 in homogeneous coordinates. And then you are truly ambidextrous. Also, you see in the conventional twistor string, you would only ever allow vertex operators that were functions on twistor space. Whereas here it's clear that somehow you express it this ambidextrous way. You've got to allow cohomology classes from dual twistor space as vertex operators. So I should just say, for those who are less stringy, of course these vertex operators here are really just couplings to a Yang-Mills field. You add that into the action. The J is a current algebra on the world sheet, but you're just saying you've got some spinors on the world sheet that couple to the bundle, is usually the way you think about it. Anyway, so with just V's and with n equals 4, you get the standard twistor string. But the question is, can you do it maybe even non-supersymmetrically with both V's and V tildes? And well, you can run through a calculation. So you can, for n to the k MHV, and this could be completely non-supersymmetric now, you want to have k tilde vertex operators. I should apologize for all the typos I now see. K tilde vertex operators, so you take a correlation function of k of those and n minus k of the untilted ones, and you just do a string path integral to do the correlation function. And there's a trick here which already played a role in the 10-dimensional ambitwisted string, whereby, well, first of all, you use momentum eigenstates. So it turns out that these are the correct momentum eigenstates to use. So this is just a statement about the Penrose transform and so on. And you then think, well, how on earth am I going to take a correlation of all of those things? You've got these horrible delta functions, and the mu's contract with the lambda tildes, and the lambdas with the mu tildes. It's going to be a horrible mess. But you can take the exponents into the action, And if you do that, we then find, instead of getting the condition that the W and Z should be holomorphic over the Riemann sphere, we get source terms just for the lambda part, the momentum part. So we get a source term for the lambda given by the self-dual fields Vk plus 1 to Vn, and for the lambda tildes from the other fields. And we can solve these equations. The mu's still remain holomorphic and will vanish because everything has weight minus 1 on the Riemann sphere. And so mu and mu still vanish, but the lambdas are given by these sorts of forms. They have to have simple poles to solve these equations here, these sources. Okay, and then when you do that, you've essentially done. You are down on an amplitude formula. The current correlator gave you this so-called Park-Taylor factor, and this now gives you a formula for amplitude, for the amplitude. And this gives you essentially a formula that Witten arrived at back in 2005 as a parity invariant massaging of the original RSV twistor string formula. It's rather tidied up. He had lots of van der Waals and things there, but if you can absorb them all into the way in which we defined the S's and things. So one of the nice things about this is that this imposes a version of the scattering equations. Already back in 2005, Witten was observing that these equations applied the scattering equations. But as it stands, it's actually giving you a refined form of the scattering equations, telling you which of the, sorry, there should be a sigma I there, which of the points corresponding to self-dual field insertions and which ones corresponding to anti-self-dual field insertions. And this version of the scattering equations only has an Euler numbers worth of solution rather than the full n-3 factorial version of number of solutions. So it gives you a refinement there. Okay, so can you do gravity? Well, the answer is yes. You adapt. So David had a beautiful model for n=8 supergravity in twistor space, and essentially you look at this model and you can see, well, actually, it's we can play the same games with that as we could with the original Yang-Mills version. And so basically what he does, you need to break conformal invariance, and this is done by introducing this so-called infinity twister, a skew twister, and we just introduced this notation, bracket notation for the contractions that come from that. And you need to introduce a whole new bunch of Z and W have superpartners, rho and rho tilde. And just, Dave's a clever guy. He just says you've got to gauge all these fields, and so you just do it. And you see what vertex operators are invariant, and you end up with these vertex operators for gravity. I mean, we all knew that they had to come from homogeneity degree 2 functions on twistor space. These are the things that Penrose transform to linear gravity, and you get these formulae for the vertex operators. You can then run through the same calculation as we did on the previous slide, and essentially the calculation runs through almost identically, except for the fact that this Park-Taylor factor that we had from the current correlator gets replaced by a Hodge-like determinant. So this, by that, all I mean is it's a det prime. It's a determinant of a matrix which has 2 degeneracies, and so in order to actually get something sensible, you have to eliminate 2 rows and columns and divide by something. But anyway, you have this det prime of H, where the H is just given by a very simple formula in terms of the infinity twister acting on the twistors here, and the sort of inner products of the spinners. Sorry, the sigmas on the world sheet. So this is actually a very beautiful formula. Sorry, before I go on to the issues, I mean, I think these are lovely formulae, actually. I mean, collaborators were saying, oh, they're very close to existing formulae in the literature, they're sort of I think Song He had something which was quite close to the, I can't remember. But anyway, but there are no moduli here. In the original twistor string, you've got to enter the KMHV, you've got to integrate out 4K moduli. And sure, you can sort of do it, and here you've essentially, but you've still got 2n moduli. You had those as well. And what you can see that they're doing actually is that they're doing a kind of, that those moduli have to be playing the role of the Fourier transform of the twistor cohomology class. So the dual, we've allowed twistor and dual twistor cohomology classes, and they're all sort of roughly speaking positive homogeneity. And what those moduli have actually organised themselves to do, without any instruction from us, is to do the Fourier transform from twistor space to dual twistor space. When I say Fourier transform, this is the twistor transform. It's a complicated object, but it does it. And so that's a sort of remarkable thing that the string theory knows how to do that. So I think these are very pretty formulae, but there are issues, and I've tried to preempt most of David's criticisms. I don't know if I preempt them all. So the anomalies only clearly vanish for the n equals 4 Yang-Mills, and even then, I guess you'll say that there are probably some. I mean, n equals 4 Yang-Mills case is sort of essentially the same as the Berkovitz-Witten model, and it has whatever problems that model has. And the n equals 8 case for gravity. But then, of course, if you do go all the way out to n equals 4 and n equals 8, you superficially at least have a doubling of all the fields. You could sort of somehow describe that their twistor and dual twistor description is the same, but you superficially have a doubling. So that's one issue. We actually imposed this condition that Z and W both were spinors on the world sheet, so the gauging of that constraint though would usually suggest that you should allow all possible sort of weights. And so one way around that is to say, well, maybe we can impose these conditions globally rather than locally through a gauging. And I think Nathan was sort of happy with that, but I'm not sure that Nathan Berkowitz was, but that was maybe an appeal to authority rather than completely clear understanding. Another way around this is to say that all degrees actually play a role, and they all give 0 except for the -1 case, when you have less than maximal supersymmetry, or those for the twistor string, when you actually allow maximal supersymmetry as well. So I think we've proved that in some cases. Or you think you get them twisted? Sorry, Yvonne knows more about this than I do. Sorry, you're squirming now. I don't know if you want to.
Some of them are 0, but not all.
Yeah, but we haven't sort of settled it. No, okay. Okay, so how do you extend this to loops? Well, we have a similar problem with the twistor string. How do you extend that to loops? I know Louise and Peter have done some work on that and so on, but I don't think there's anything that really definitively extends these ideas to loops in the standard twistor string. And similarly, Arthur and Volker Schomerus have a genus 1 formula, which I guess, I don't know how well tested that is now.
It has the right IR singularities and some version of modular invariance. It has some nice properties, but it's very hard to match it onto to show that it's an actual supergravity integram.
Right. Okay, so anyway, so there's some sort of progress there. For me, really, I mean, the thing that I found extraordinary about these formulae is that in some sense this is a perturbative general solution in a very, very compact form. You imagine it expanding out sort of just ordinary Yang-Mills or gravity in space-time, and you just get a complete mess. And everyone knows this is probably a double factorial mess if you do this in terms of Feynman diagrams and so on. And you start to think, well, maybe there's some smoking gun here for something nice happening for the nonlinear backgrounds. And the big problem here is the characterization of the field equations for nonlinear backgrounds that relates to this theory. I mean, I've talked about the formal neighborhood story, but that's not really a usable characterization, whereas these explicit formulae do look like they ought to give rise to something that is genuinely usable. And I guess related to that, we just pluck those vertex operators out of the air. So so one of the things that I find puzzling is that the old story about formal neighbourhoods just has a complete mismatch, really, with this story. The supersymmetries that are critical to this story are n equals 4 and 8, whereas those don't seem to be playing a role for the formal neighbourhood story. So that old story somehow seems to be irrelevant to this. This story, of course, extends to all dimensions, which is nice, and it may be that there's something underlying this story that we need to learn to actually say something about full nonlinear ambitwistor spaces for full nonlinear spacetimes. And I think there's still some hope that it would be possible to do something there where there's. I think these conservative formulae are a smoking gun for something really nice happening there, but I don't think any of us really know how to push that through. Okay, so anyway, so we get these new formulae, so they're very nice, and they can be proved really just by comparison to the original twistor string. And but you now have a framework that's valid for any degree of supersymmetry, and so you can worry about the fact that they're anomalous or non-critical, except with this too much supersymmetry, the n equals 4 and 8. But maybe you would think about the other matter fields being required to make to write. String theory only works in 10 dimensions. If this is somehow a friend of string theory in the same way that the 10-dimensional ambitwistor string is, then maybe in some sense you really have to think about the way it is reduced from 10 dimensions in order to see how you could get a genuine anomaly model. This formula can be compared to the CHY formula. One of the curiosities is that this Hodge determinant here, you can see directly from the comparison between the Yang-Mills and the Grabsy formulae that that this Hodge determinant here is the 4-dimensional reduction of the CHY Pfaffian with that MHV degree. And there should be some relationship between the string field theory actions for these ambitwistor strings and just a regular ambitwistor action. I mean, so these are all things. Maybe one day all of these corners will be filled in. We'll know how to solve the Einstein equations on the nose in ambitwistor space, and there will be a nice ambitwistor action, which we can also understand as a string field theory action for this ambitwistor string, which allows us to understand that that's. I think people will say that's over optimistic. I'll stop there.
Say a few words. What's the most modern understanding of why ambitwistor string captures scattering amplitudes? What makes it known about correct scattering?
What makes it?
Well, explanation why ambitwistor string is able to reproduce formally scattering amplitudes. Is there any understanding of this, or this is just a fact?
Okay, actually, that should be up there on my list of puzzles. I mean, so there is a traditional approach to writing down scattering amplitudes that comes from sort of alpha prime goes to 0 or high tension limits of string theory, in which as the tension goes up, your string gets narrower and narrower.
But I don't understand the question. Well, why does string theory capture scattering amplitudes in whatever theory that is?
Yeah, no, but I mean, that in itself is okay. So let's step back a bit. I mean,
wall sheets become Feynman diagrams.
Yeah, that was what I was about to say. Was that world sheets coming from the diagrams? But I think in many ways, despite that being a mantra that we've been hearing now for sort of 40 or 50 years, I don't think there's a proper mathematical understanding of it. I mean, it's very much an immersions understanding which you can push through in examples. But I don't know. So Peter, you.
So I couldn't understand. I couldn't hear actually most of the discussion.
Understanding
Oh, sorry. So this is just the question as to why it is that these actually give rise to scattering amplitudes. And so it's obviously very closely
understanding that in ordinary string theory, where it's quite clear.
Well, you say it's quite clear,
Yes.
but I mean, you say that clarity comes from the world sheet degenerating onto Feynman diagrams. But
It comes from taking the zero slit limit.
yes, but
What's wrong with that?
well, because it's
I mean, there's certainly a clear understanding of the level of classical equations of motion, right? And the classical
There's
equations
understanding at the level of the amplitude, so you can just calculate.
That's
Yeah,
what Shirk
sure,
originally
but-
did. Okay, but I mean, that's
different
nuts
from
and
the
bolts.
twistor string.
Yeah, okay, that's also true, yeah.
So I would say there's a very clear understanding which has existed for 40-some years, back to Shirk, as to why the zero slope limit, the tension limit of string theory gives particles, description of particles, but there's no such understanding of why that happens in twisted string theory, as I understand it.
Okay, but even there, I think,
Even where?
even in the space-time description,
Of what?
the Shirk type description,
Yes.
I think somehow it's a very,
What's wrong?
well,
Just take the limit, it's there. There's no doubt that it reproduces amplitudes.
Exactly.
Why?
Yeah, I mean, it's
It both does it mathematically if you look at the amplitudes and take the limit, and also it's extremely physically plausible. That
it is. Yeah,
and the
it's
tension
very,
goes to
very
infinity,
physically
the thing contracts to a point.
but that's
So why is
missing.
it?
Would that persuade the mathematician? I mean, I think
Well,
there's also the non-linearity.
The
is very
mathematician's going to be
difficult.
convinced, presumably, by the fact that it works with the amplitudes rigorously. You write down the amplitudes, you take the limit, it's a mathematical fact.
But I think all the time you're using uniqueness theorems. You're showing that the
Using which theorems?
uniqueness theorem. So you're saying that if it's gauge invariant and it has these properties, it has
Just
to be
write down,
Yang-Mills.
write down the amplitude. It's an actual mathematical function. You take the limit.
But there are all these gauge. I mean, so you take the limit, but what gauge does it give you the Yang-Mills Feynman diagrams?
Well, we do it for the start. We do it in phi cube theory.
Okay, so if but for Yang-Mills
Shirk's original
gravity,
paper was in Shirk's original paper was in phi cube theory.
okay, so for phi cube theory, I see there's no ambiguity. Okay, well, that's fine. Okay, but I start to get queasy with Yang-Mills and gravity.
I think you could cure your queasiness if you took the right medicine.
Okay, I haven't read all these old papers.
Well,
of course, so,
that's in the paper by Shirk and Levert.
right. Okay. Sorry, you did refer me to these before, and
But I really don't think there's a problem.
Okay, no, I'm not saying there's a problem. What I'm saying is that there's maybe not the best way to understand. You don't necessarily have the most crisp mathematical way to understand this correspondence between string theory and field theory.
Well, crispness is probably in the ear of the beholder.
Yes. No, I would take that, okay. But yes, okay, so the twistor theory adds an extra layer of obfuscation on that. And
What is the status in the gravity example? What is the status of the tree amplitudes that come from that construction? Are they known to be
yes. Yeah,
that's been
good.
proved?
Yeah.
By whom?
Well, I guess because it has a Skinner formula was proved by BCFW recursion, I guess by the sort of three of us, I guess you two did.
By what? I assume here.
By BCFW recursion, you can show that the formula that I wrote down with Freddie, it's manifest that it's got the right three-point amplitude, symmetry, bar, it's trivial. And you can use BCFW recursion to show that the remaining formulae are also true.
Does that work without supersymmetry?
At tree level, I suppose it does. As long as you do the right BCFW shift.
And then these formulae are equivalent to that formula.
And that works in any dimension?
No. So I mean, the CHY formula, I guess, are now known to be true.
Yeah.
Gravity.
But as far as the string thing,
Yeah. So these are specific to four. These formulae, at least in the second part of the Lion's talk, are specific to four dimensions. And so with the gravity twistor strings, that I don't know that I would claim that we understand the world sheet model as well as we'd like in either of these framework versions.
No.
But it is true that you just, you write down a complete list of every possible vertex operator, you compute the world sheet OP of insertions of these, and you throw away no terms, you keep absolutely everything, and you get these formulae which are proved to be true. Right.
what was the statement about the anomalies vanished only for n equal 8 supergravity?
Well, this is a calculation I did with the gravity twister string version.
I mean, these are just two of the anomalies, and I guess there are plenty more.
So the point is there are some other fields on the world sheet which carry charge under the GL1, the scaling symmetry of the twistors. So it's no longer true that you want the fermionic and bosonic parts of the twister to balance that GL1 anomaly, because there are some other fields that also contribute. And when you take into account everything, you need a fermionic.
But your statement is that even if you don't have that supersymmetry.
Oh, well, your claim was if I take, sorry, my claim was that if I take the formula for the amplitudes
Yes.
and I restrict to external states that are just pure gravitons, not n equals 8 supergravitons,
Yes.
do I get the right gravity tree amplitude for pure gravitons? And the answer is yes. I don't know how to get just that non-supersymmetric story out of a world sheet model. But doesn't mean explicitly that there might be some guesses you can make. Yeah, I mean the world sheet model most naturally works with n equals 8.
I mean, it certainly looks like a miracle that those anomalies are vanishing for n equals 8. I mean, I don't know if there's a way in which it seems less miraculous. But of course, he doesn't.
20 models I wrote down before I wrote that one down. It wouldn't seem like quite such a miracle.
But it doesn't have a BC system in it, and it ought to.
The amplitudes,
So-
the amplitudes that come from this string that you have, and that string is only is anomaly free for the supersymmetric case. And the amplitudes, the tree amplitudes,
Depends which anomaly, right? If it's just a conformal anomaly, it
tree
shouldn't matter.
amplitudes must involve some.
Well, if you specify external states to be pure gravitons,
Then there's no.
then there's no internal fermionic stuff, even in finite diagrams. So you can't tell the difference at tree level. If we were able to understand, and afterwards made some progress, but if we've been able to understand this story at a higher genus, or one loop, or whatever that would correspond to, then of course you see the difference.
Siegel's work on the chiral string, he was finding that there were some hidden, divergences which led to Z-bar dependence coming in something which looked like it was naively holomorphic, or was holomorphic classically. And that seemed to play a role in the quantization. And if there is something like that going on, would that affect the results you were getting?
I think that's over to Eduardo or Piotr. I don't know if they've studied these things.
Oh, I'm not familiar with this.
Yeah,
What paper are you talking about?
And they're saying that, Siegel was claiming in his recent paper on the chiral string
Right.
relationship with ambitwistor strings and so on, he was saying that there was some infrared divergences, and these infrared divergences led to, when you looked at the careful quantization, they led to some Z-bar dependence and things which naively think were holomorphic. And that played a role in some of the
well, he was
subjects.
doing the wick rotation. He's doing this very weird. Sorry.
The way he gets rid of the anti-holomorphic part is a little bit suspicious, but the whole thing, the whole idea, which he does without really saying it, is I suppose right, that you have this different quantization, and the string ends up being chiral. So in practically, the way he achieves getting rid of Z bars in the string amplitude is a little weird, but I don't know what he thinks about it himself.
So I think Eduardo is going to do the second half of this talk in about, say, do you want to start in 10 minutes, course, for that?
Here?
Well, here is probably better than doing it in the common room.
Yeah, fine, but it's, there's not, yeah.
Sorry, I mean, is that what other people want?
I don't know how many you have.
Sorry?
Do you want me to give
It's
from
not-
the beginning in or
we'll just
just?
carry on
No, no,
the
no, no,
discussion,
second
because-
half, second half.
Sure,
The
there's
part
not,
you
there's
missed.
not that much to say, but.
Or would you want to leave it till half past? and then-
No, it's fine.
Yeah, okay. Sorry.
Thank Lionel
Sorry.
again.